Gary Hudson. I'm the head of data science and AI at a company called Draper and Dash. I previously worked for NHS. So today I'm going to be looking at advanced modelling in R, so the potential of R and ML in healthcare, predominantly focusing on supervised machine learning. AI, ML, what's the difference? These terms are used a lot interchangeably. So artificial intelligence is basically training machines to surpass humans. Not quite there yet. Have a look at Moore's law. It shows you currently we're about the potential of a rat's brain. By about 2025, we'll be probably starting to compete with ourselves as sentient beings. In terms of machine learning then, so this is the study of computer algorithms that allow computer programs to automatically improve through experience. So keep performing a task until they get it right, essentially, because computers are relatively stupid at the moment. What makes up AI? So there's lots of facets of AI. So we've got, obviously, on the machine learning branch, deep learning, supervised and unsupervised machine learning. At the moment, we're going to be focusing on the supervised machine learning branch. In terms of natural language processing, there's things like content extraction, classification, sentiment analysis, topic modeling, machine translation, so translating things into different languages, that kind of falls under the deep learning branch. Question answering, things like Alexa, text generation. In terms of computer vision, image recognition and machine vision, so classifying objects, developing surveillance systems, etc. Speech to text, so analysing the cadence and tone and inflection of people's voices and being able to then use the words that they actually speak and to put it into text. Planning and robotics are a branch of reinforcement learning, which I'll go into the next slide. So machine learning then, it's comprised, as I've said, of supervised, unsupervised and reinforcement learning, as well as deep learning. Supervised learning then, so classification and regression are going to be the focus of today's webinar, and we're also going to look at how you can deploy that in a package called Caret, which is a really popular package in R for machine learning, and one that I favour as well. In terms of unsupervised learning, so there's things like clustering and dimensionality reduction. So clustering's used a lot in like patient acuity segmentation, and it's used a lot in marketing. Dimensionality reduction, if you've got lots of features, so lots of underlying features like thousands that might cause a machine learning model to run really slowly, we can perform that, but that won't be the focus of today. Reinforcement learning, so looking at game theory and how you can navigate through different game environments and how it can solve game environments. When I first learned this, I learned it with Doom, and it found actually by continuously learning, the best path through a level was just to avoid all the bad guys and go straight to the end. So R versus Python, the great debate. So what's R good for and what's Python really good for? So R is good for supervised and unsupervised learning. There's lots of packages out there, Caret and lots of unsupervised packages as well. Natural language processing, so a lot of you will be aware of tidy text packages and the text mining package. Read lots of blogs around Julia Silge and David Robinson in terms of the tidy text package. Deep learning, so this has been made available for a couple of years now in R. Packages such as H2O have been there for a long time, Caret and Amazon's MXNet. R is really good for data wrangling, encoding, cleaning, visualizing. Tidyverse is your go-to for that. In terms of Python, that's good for all the same kind of reasons, but it's got a lot more in it under its natural language processing hood. In terms of computer vision, Python's still superior. It's got a package called OpenCV, which can be used to perform face detection on web cameras and video links. So that's how you can develop live surveillance systems. Again, we're looking at that something at the moment in Draper and Dash. Data wrangling, feature encoding, again, similar kind of capability in Python with NumPy and pandas and all that kind of stuff. Reinforcement learning, so to build those models, really, there's lots of examples in Python, not so much in R. And there's lots of code examples as well. Plus, the object-oriented platform in Python is a lot easier to understand than R. So how can ML be used to aid decision-making in healthcare and challenge organisation issues? So how we're using it at the moment, there's lots of other examples of where it's been used, just need to Google. But how we've been using it in Draper and Dash. So the first example is we create a lot of decision impact support tools and capacity and alignment tools. So that deploys supervised learning and augments existing VI solutions. So what we've done currently is deployed omission prediction tools, readmission avoidance, length of stay prediction, mortality predictors. Looked a lot around COVID-19 as well, and that's something that we're doing currently. Imaging augmentation tools to aid like radiographers, so computer vision algorithms utilized to detect irregular scans, cancer, presence of certain conditions, using something called convolutional deep learning. Deep neural networks are used a lot of the time if we don't know the features that we want to encode beforehand and want to expose hidden relationships in the underlying data. And again, reinforcement learning is something that we're looking at in terms of optimizing prescription regimes. In terms of wider usage, I'll just leave this slide here, whereby things are actually utilized. But in healthcare, it's been used a lot in disease prediction and effectiveness of medication. Supervised learning then, so regression and classification, what's the difference? So regression, as some of you will be aware, it's just trying to fit a line of best fit through a series of data points to make predictions. Classifications, trying to find the best separation between those points and fit in a kind of decision boundary or a classification boundary between those points. And there's lots of different algorithms that do it in a different way. We'll explore those in depth in the practicals in a short while. Supervised learning, so what is it? So it takes the training data, so the input data, does a lot of feature extraction. So we do all the dummy coding and data manipulation and feature encoding beforehand. It's then we look at then how to evaluate the training data. So we partition it into test and train splits, test, train and validation, or k-fold cross-validation splits. I'll explain those in great depth in a while. We then pass it through a supervised learning algorithm or algorithms. Algorithm is then trained on labels, so it could be whether a person's discharged or not, whether they're stranded in the hospital, whether they're going to be readmitted, etc. The goal of a supervised learning algorithm is to predict Y for inputs Xi, so for lots of different features that might predict that Y. Predictions are made on the labels. This could be what a class no X will fall into, so classification, or what the value is predicted to be, regression. So I'll take you through now in R Markdown how to build a machine learning model with the Caret package. I'll just switch between my screens. So first of all, what we're going to do is load in the data. So this can be loaded via any different package that you use. This is a very simple and synthetic data set that I've composed for the sake of this tutorial. So it takes patients who have been stranded or not stranded, or who are long stay patients in hospital. And it uses features such as their age, whether they've been referred by a care home pathway, whether they've been flagged medically safe, whether they've come through HCOP, arrived on the weekend, whatever. This is not an exhaustive list of features. I would endeavour you work with the organisation to understand more things that can be coded up. But essentially, we've got binary encodings. We've got age as a continuous variable. What we're then going to do is look at the actual classification balance. So we've got a balance of those that are not stranded. So that outweighs, it's about 60-40 split currently. This would be a lot lower with real data. So what we've first got to do is deal with that class imbalance, because what the model will be good at is actually estimating those that are not stranded more so than those that are stranded. So it'll pick up the features of those that are not stranded over those that are stranded. So dealing with classification imbalance then, so there's a technique called SMOTE, so synthetic minority oversampling technique. This can be used to rebalance an unbalanced classification. So essentially what you're trying to do here is look at the existing points in the minority class, and it looks at the radius around those and uses distance metrics to sample the points closest to it. So if that point lies closest to this minority class point, it will be replicated and it will be synthetically generated. Again, this is not advisable with massive class imbalance, but it can be used if there's something like a minimal imbalance like 60-40 or even 80-20. If the class imbalance is something like 99 to 1% of the thing you're trying to predict, then I'd probably think you need to go back to the drawing board and look at sampling techniques. Anyway, to implement this in R, we're going to create a variable. We're going to pass it through the SMOTE package. We're going to estimate the stranded label, so the thing we're trying to predict. Tilde, so with everything else in that data frame. So that's a lot of people have used this if they've done any modelling, but it essentially says that's the thing I'm trying to predict, and they're all the other features that predict the thing I'm trying to predict. It uses the data frame, and then you can estimate, or you can put a percentage over that you want to oversample and undersample by. You can then drop that. You can then put that into a data frame. You want to drop NAs because machine learning models don't work very well with, don't work at all with null values or NAs. We're then going to see how this has addressed the imbalance. So you can see that now we've got more of a, it's inflated a little bit the non-stranded, but now the stranded are starting to match. So that's going to be a really good way of training our algorithm with similar features, because it'll have a lot more replication of those underlying features, say a lot more of patients of a similar age, etc. The next step is to scale and standardize your data. That's something that I advise with all machine learning models, and some won't work if you don't do it. So this is implemented. So what it does, it takes all your raw data that's distributed quite widely, and it'll scale it and normalize it. So it's more of the same scale. So it'll put things like continuous variables onto the same scale. It'll put dummy codings onto the same scale, etc. So a way to do this is use the pre-process function in Caret. So we're going to balance the stranded. We're going to drop NAs again. We're going to use the pre-process function prior to that. We're going to use the balanced stranded data frame, and we're going to use all the features in that data frame to do the scaling of it. And I know that the thing that I'm trying to predict, so whether it's a long waiter or not, is in the first column. So I'm going to go from column 2 onwards. And then I'm going to predict what this looks like and give a summary of how that's been applied. So you can see that's worked correctly. So the next thing to do is join that data back together. So we're going to have the original label from the original data set, and we're going to actually bind it to those variables that have now been transformed and centered. We're going to rename the levels because I think I had a space in the levels to make them valid for using in R. You can also use the make.names function to do that. So now, how do we evaluate a machine learning algorithm? So there's a couple of different flavors that you can use to resample and reevaluate and evaluate a machine learning algorithm. So you can use holdout splitting. So that's a train and test split. You can do train, test and validation splitting and k-fold cross validation. This is a visual just to show you how that works. So you get all your data. The simple solution is to do a train and test split. There's a lot of literature to say the kind of optimal levels are around about 75 to 80% training data to test. Again, but this is a bit more of an art than a science. Or you can use cross validation, which essentially goes across and takes different training sets and different test sets across each of the splits and each of the folds. I'll show you how that works in practice later on, and then essentially you can do a final evaluation with your test data or the validation data set. So to create this split here, the training and test, we're going to create a data partition in the Caret function. We're going to use the stranded label, so the long waiter label. We're going to set it to 75% split in the training set and 25% in the test split. And to implement that, we just basically say, take the rows in my index of 75%, and it will do it randomly, the 75% in that split, and then give me the inverse of that, so the other 25%. Examining the dimensions of the data frame, you can see that it's obviously got a different number of rows, but they've got the same structure in terms of columns. That's important. So now what we're going to do is train an initial model on our training data set. So we're going to set the accuracy. So we're looking at accuracy because we've got a balanced data set. If it was a really severely inaccurate balance, we'd probably want to use the ROC curve instead. But here, now I've done class imbalance and I've solved that problem, we're going to use accuracy. We're going to set the random seed to make the results reproducible. So this is, if you run this algorithm again on your own PC, you'll get the same results as I do. In practice, you probably wouldn't set this if you weren't doing a demonstration. So the main driver behind Caret is the train function to train a machine learning model. This is a standardized way of model training. So I'm going to take the stranded label. So I'm going to take the long waiter, or should I say, whatever it's called. And we're going to use all the features, all the other features in that data frame as the kind of independent variables. We're going to use the training data set that we've just partitioned. We're going to specify one of the model encodings as naive Bayes. Caret's got a number of models. I'll put a link in the presentation. There's about 250 models currently in Caret. We're then going to run that and it gives you the output of that model. This will give you a numerical 0 probability. It does that on the naive Bayes models if it's got very low variance, but it still means it's usable. The results are usable. Again, you could suppress that warning if you wanted to. So now we've got this, the model trained. So that will take about 5 minutes. That's why I've got it in the R Markdown file. Now we've got the model trained. We're going to predict on the test set with the test set. So you can use the core predict function. So we use the model that we've just trained, and we set new data is equal to the new test data frame, so the other side of the sample. And there's two different types that you can use in classification. There's a probabilistic prediction, so the probability of belonging to a class, or a raw prediction, which will be the class label. We're going to use those predictions and combine them into a predictions data frame. Okay, so next step is to evaluate the predictive accuracy with a confusion matrix. So I've put a link to the confusion matrices in my presentation, and I'll step back to that after this tutorial. So we're going to build the confusion matrix object. I'm going to use the confusion matrix function from the Caret library. We're going to specify the class label that we've predicted, so naive Bayes class. So that's the prediction against what the actual label was in the test data, and I've specified I just want to return the stranded label. I'm going to also set the positive value to a long dot weighter as well. And you do this because sometimes if you don't, the confusion matrix will be upside down. So as you can see, this is a very low sample, and with machine learning you'd have a lot larger samples than this, but I've included it in the sample files just so it runs much more quickly than a data set with 1,000 features and 1,000,000 rows. So you can see that long weighter, it's really good at estimating that. So it's got 182 right with 4 incorrect. So because we've done that imbalancing and we've done some synthetic resampling on the training set, we've started to get a real good representation of that underlying data set of the long weighters. We can now see that the accuracy is pretty good actually at 83%. We're going to try and improve on that in a second. But what we're really looking at is sensitivity, so how good it is at actually predicting whether it's going to be a long weighter, and that is really good. In terms of specificity, and again, these metrics are explained in a blog post, and I will link back to the presentation after we've gone through this markdown file. The specificity is not as good, but the balanced accuracy is really good. It's around about 82%. So, okay. Now, if I want to visualize this matrix, there's nothing inbuilt into R at the moment that I'm aware of that does this very well. So this function that I've created here will work very well on a binary classification task. So there's 2 dependent variables that you're trying to classify. I've put a link in. We won't get time to cover this on 04, which is the multi-class classification project. It shows you how to implement that in Caret as well. But essentially, you just pass in the confusion matrix parameter that you have just built here and the classification labels, and it gives you a nice graphical output of what the results that confusion matrix look like, as opposed to just getting the console output. In terms of variable importance then, so looking at global variable importance, I've developed a function that can be put into your projects that you can use. It essentially just produces a variable importance plot. So you use the model fits, and then you specify which predictor you want the variable importance for. So there'll be long dot weighter or not dot long weighter, which is the kind of inverse of that, or whatever you're trying to predict. And it obviously this data is synthetic, but it will allow you to show which features significantly affect your overall model. In terms of looking at local interpretation of the importance at a patient level, there's a package called Lime. This works really well with massive data sets, not so much on smaller data sets, but there's a vignette there and a link to show you how to implement that into your project. Won't go into that in any greater depth. In terms of algorithm benchmarking, so what we're going to do is we're going to use now a different resampling technique, the repeated cross-validation. So it will basically implement this to a 10-fold essentially. So take different train and test splits. And we're going to do that 3 times. We're going to repeat it 3 times with 10 folds. So again, I'm going to set my random seed for each of these models so you can get the same results as me. I'm going to train it on a recursive partitioning tree. I'm going to train it on a logistic regression model. I'm going to train it on a random forest. And then this is the important part, because we're doing it more than once and we're resampling. We need to use the Caret resamples, and these need to be passed in as a list. And we then can call it whatever we want, all part fit, logistic regression fit, so long as it links back to each one of the models that have been trained. Then we're going to summary those resample results and look across which is the best estimator or which is the best model for my particular problem. You can see that random forests are actually far surpassing the results of my naive Bayes model. We're getting with up to a maximum of 93% accuracy. And more importantly, because I want to put this into production, the kappa rate's really high as well. It's at 86%. So Cohen's kappa means if I'm using this with unseen data, how well, it's kind of a benchmark of how well it will perform in the real environment. I'm going to use the lattice inbuilt functionality. So I'm going to call the dot plot of the resample results. This allows you just to view what we've just seen in the console output visually. So we're going to choose the random forest model. So one more thing that I could do or two more things I could do to improve my machine learning model, classification model. I can do hyperparameter tuning. So inbuilt into Caret, there's two different search types. You can do your own manual one using grid extend, but I'll use the kind of inbuilt ones for now, because I've done the manual tuning before and found that actually Caret's defaults perform a lot better. So what's the point? So grid search and random search, they use gradient descent to optimize the number of parameters. Again, you can look up gradient descent, and I'll put a link to some resources later on. So Caret's random search method is quite easy to implement. So again, in the train control as part of the Caret functionality, we choose a method of resampling. We choose what we want to do with that resampling. And then we just extend that with using a search parameter. So search equals random. So I want to implement a random search. Then I'm going to build my random forest model again using that random search. I'm going to print the results out now and see has that been optimized. So I'm using a very simple hyperparameter tuning estimation. You could do things like estimating the optimal number of trees to be built as well. But for sake of example, I'm just going to try and optimize the number of random variables to split on. And you can see actually the 3 variables seems to be the best accuracy. So, you know, we're going to go with that. We're going to trust Caret's inbuilt logic to do that for us. And again, if you wanted to just view what that's actually done in terms of the random search, you can see it across. So it's optimized the number of randomly selected predictors. So the number of randomly selected predictors, or the mtry parameter, should be set to 3, because that's going to give you the best estimates. The grid search is implemented very much in the same way. You just change the random for grid, and then this will optimize as well through the grid, and it also tries to optimize the number of randomly selected parameters, i.e. the mtry metric in random forests. It's worth noting that the hyperparameter tuning will tune relevant to the specific algorithm you choose. Because we've got random forests, this is mtry, but for things like support vector machines, it'll be things like cost parameters. Again, I'll show you a link in the presentation after we finish this tutorial around where you can obtain all these resources. So then what we're going to do is do the same plot, so you can see it around about 4, we're getting the best accuracy. So mtry equals 4. So now we've done our hyperparameter tuning part of the modeling. We're going to move on to building our own ensemble model. So a random forest in itself is an ensemble model, but we're going to go even further than that. We're going to actually build our own. So we're going to use train control again. Should be quite familiar with this parameter by now. We're going to use just cross validation, not repeated. The number of folds we want is 10. This time, to make it work, we need to save the final predictions of the model, and we need to also expose the class probabilities and set that to true. So it will give you the probabilities of arriving into each class. We're going to specify an algorithm list. So we're going to pass in naive Bayes. Again, if you need to refer to these, the models are here. And it shows you all the additional parameters that you can tune as well. Linear discriminant analysis, KNN, logistic regression, random forests, and recursive partitioning trees. We're going to use system time just to actually time how long these models take to run. We're going to suppress any warnings. I'm going to create a variable called stack models and pass it through as a member of the Caret ensemble package. the Caret list parameter. We're going to use the stranded label, and I'm going to pass in all the other independent variables. I'm going to pass it through to that data set. We're going to set the train control equal to our train control and a method list equal to all those algorithms that we've passed through. Then the last step is to use something called a metaclassifier, and I'll explain this in the presentation in a second. We're going to use the Caret stack method from the Caret ensemble. We're going to use the stacked models that we've just created here. And we're going to use pass the method is equal to random forest. And again, all these resources will be available on the NHSR Communities GitHub site. We're going to use a random forest. So in this sense, it's an ensemble of an ensemble. We're going to then print out to the console the results of this ensemble. And we can see actually now we've got good accuracy still, but probably the original random forest performs just as good. But if you didn't have random forest as an option, this is how you build your own ensembles in Caret. Then, because everything's stored in a list, you can expose each element of each list by using the $sign notation. Once we've got our best model and we're happy with it, so this one's pretty good. It's about 97. It was about 93% accurate at predicting whether a patient's going to be a long waiter. We're going to push this out into production. So I want to save this as a production model. And say I train this every week to pick up any differences in underlying features, underlying parameters. We'll save the ensemble object, the data set object, and the data frame, and I'm going to save it in a file under the models architecture as the ML production model for classification.audio. So just flicking back to the presentation then. We've built a classification model in Caret, and again, please refer to the R Markdown files and the resources that come in the GitHub repository. We've been through the machine learning process. We've actually now, because we saved that model out, deployed the model for use in the live environment, and I'll show you that as example 3, how you then use that with real-time unseen data. So that then starts classification modeling. So we went through SMOTE and data scaling and data partition and resampling. Again, if you need a good underpinning of all the algorithms mentioned here, I would really recommend this book, An Introduction to Statistical Learning. And I've also provided a free link. If you just click on the book, it will take you through to the website where it's located as a PDF. And that will take you through all the algorithm logic and intuition and the mathematics behind it as well. Again, I normally run this as a 2-day course. This is being done in an hour. So you can appreciate I ain't got time to do the algorithmic underpinning. In terms of the algorithms, that's just a link to the R models that you can actually train in Caret. In terms of confusion matrices, I put a link into a company blog I did around confusion matrices and helping people understand those and why measures are so, more important than others when you're evaluating what and when what to deploy, what answer to a problem it's trying to solve. In this instance, we're trying to predict long wait patients. Then the add-in that I've got in the functions file is the confusion matrix and the variable importance. We've just covered the algorithmic benchmarking and hyperparameter tuning. In terms of the stacking ensemble, we went through all those different models that we created at different levels, taking the original data, using all those models to stack the results. The predictions from these models then become the features that are then fed into the Metaclassifier. Then the Metaclassifier makes the final predictions based on the predictions from the other model. Now we'll just step into the regression modeling. I'll skip over the first couple of stages of the process because we've already done that in the classification side. So again, this one is an example of the ability to predict the time to be seen, looking at loads of ED metrics in the actual front door environment. So looking at things like whether it's an urgent patient that's been referred in, whether they're coming by ambulance, police escort, etc. When they've arrived on weekends, what the gender of the patient is, and their time to be seen in minutes. The algorithm then will pick up on these time to be seen and these features and try and make a good prediction of that. In terms of feature encoding and scaling, I've been through this in the classification model. And again, regression, machine learning algorithm benchmarking, I put links into interpreting root mean squared error and mean squared error. We'll take you on to setting the evaluation harness. So we're going to do the same thing as setting the training control with cross validation with 10 folds. And we're going to set the metric this time to, because it's regression, root mean squared error. So this will iterate through, we're going to essentially compare quite a few models. So I'm going to set the random seed again, so it's your results the same as mine. We're going to use a linear regression. We're going to use an elastic net regression, which is a combination of lasso and ridge regression. We're going to use a least angle regression. We're going to use a neural net, a simple artificial neural network. That's trying to converge. That's why I've got lots of outputs there. I'll just skip through the results here. And then we're going to train a support vector machine with something called a radial basis kernel. And we're going to do a regression tree. Notice here, though, we're doing the kind of scaling of the features on the fly. So in the model, this is my preferred way of doing it instead of doing it prior to the data set, because it allows you then just to everything that's at this point. So all the features that predict the time to be seen will be centered and scaled. And I just find it an easier way to implement in the actual Caret functionality itself. We're going to set the train control equal to the control harness we established earlier. So then, as similar as we've done prior, we're going to collect a list of those resamples. Because we're doing k-fold cross-validation, we're going to need to resample that data. We're going to use a linear model, the elastic net, the least angle regression, neural net, and just create labels as a list. We're going to use the lattice functionality again to return it as a dot plot. So you can see here actually that our classifiers, and it gives you a good way to benchmark those classifiers. Our random forest again has got the lowest mean absolute error and root mean squared error. So meaning that your results are going to be more accurate, so the line of best fit is more accurate. Your neural nets, actually your ANNs are not performing very well at all. In terms of your R squared, so the features that that are in the model that predict your outcome, your time to be seen, this would need a lot of work. And at this stage, I'd evaluate this and think, actually, we need to get a lot more features from the service and understand the service better. Again, this is synthetic data, so I would expect that your R squares are higher than that. If you want to implement this as a box plot as well, Lattice has got the BW plot where you can just get your confidence intervals and your high and low lines. Again, we'll take you through how you improve the model performance with ensembles. So I've created a function here this time, so I'm not going to step through it all. But this could then be used in your projects to deploy and use it with real-time estimation, so you can build your own ensemble algorithm similar to random forests. So it essentially takes in the Y label, so the thing you're trying to predict, or things. It takes the data frame that you're passing in. It takes the number of folds that you want to specify and a meta model name. So it does the same estimates as it did before in the classification. And I've used at the moment the random forest and the quantile random forest because they're really good estimators for regression. But you could extend that list just by adding a comma and extending your put in whatever other algorithms you want to run in that parameter. Then it passes it as a formula, the Y label, and then all the other estimates as we've seen before. And this can then be deployed in any of your live settings. To call that function that I've just created, I'm going to use system time. I'm going to suppress warnings again. I'm going to save it as a variable in memory called meta ensemble. And then I'm going to call the ensemble function. So the thing I'm trying to predict as before is time to be seen. I'm going to use the ED data set. I'm going to use the number of folds equal to 10. I'm going to use a meta model name. This is called from the known names, so Bag Earth GCV. I'm going to use SVM with a radial basis kernel. And then I'm going to plot that ensemble model to see how, and it optimizes essentially the cost parameter, which is what you use in support vector machines. And actually the best root mean squared error is at a cost parameter of 1. You can view those meta ensemble results by using your $ notation going through the list. And you can see that actually to make that estimate, that evaluation, you've got these cost parameters and these sigma values, but you can actually say that the one with the lowest root mean squared error would be the one that I choose if I was going to deploy it. However, I'm still worried about the R squared value not being high enough to actually be put into production. So for the classification model, we were confident that that was a good model to be used in production. For this one, we need to go back to the drawing board. So do more hyperparameter tuning, etc. So the final step is deployment, if you were to deploy it, and I like to save the steps and models anyway, is to save whatever you want to use in this package, this data package. So I'm going to save the ED data frame. I'm going to save the Meta Ensemble model that I built as a list, and I'm going to save it in my models directory and call it regression prod model, or whatever you want to call it, local to you. So going back to the presentation, we've then gone through the regression benchmarking and what the ensembling function, so how you'd actually use that in practice. So now how you deploy this into a live environment, I'm going to take you through a very basic example of how this can then be deployed. Again, I'm going to switch back to our Markdown. So we load the original ensemble into our new environment. So what I'd recommend is you have a train R file separate to your actual production file, because your training file will take, if it's a large data set, can take hours and hours to train, whereas this can run straight through a pre-trained model and make predictions straight away. So I'm going to load this into a new, I'm going to call it my production model, my production script, or my production model. I'm going to load in the results from the previous model. I'm going to use the production data and pass through it to make predictions. So here, because I've got no production data, I'm not working with a live BI environment, I'm going to create a sample of the original training data. And it's important that if you are creating this on a live system, the structure of the data set must match what it's been trained on. So we had 8 columns, it's got to have 8 columns in the live data and of a similar type. So I'm going to treat the original data as unseen, no unseen data. So here I'm just going to set a random seed again so it's reproducible. I'm going to sample using the sample end that data set. I'm going to take 40 observations. I'm going to select everything from that data set, and I'm just going to drop the stranded labels, because we basically on unseen data you wouldn't know what the label was. So whether they've been estimated as a long stay patient or not, long waiter, sorry. I'm going to take a head of the production data to see what that looks like. Again, these have all been encoded. So in your data set, that would also need to be encoded. So now we're going to make predictions with the unseen production data. So now we've got this new unseen data frame. We're going to predict on the ensemble, which was trained in the original classification modeling step that we did at the start. We're going to set the new data is equal to the production data, which we've just created in the previous step. We're going to set the type equal to raw. So I want the raw classification labels, which will give you this below. So whether a long waiter or not a long waiter. We're going to do the probability prediction. So I'm going to predict from that ensemble whether the probability of whether they belong to the not long waiter or the long waiter class. I'm going to take the head of those class predictions just for viewing here. The last step, if you've got a BI solution, is to combine your predictions with your original unseen live data. So that's easy done with cbind or bind cols in deployer. I still like cbind. So I'm going to cbind those class predictions together, and as you can see on your new unseen data, you've got these class predictions ready to go. We've deployed this in a stranded application, and this is the benefit of that stranded application and the trust that we deployed it at. Means that on the first day of their inpatient spell, we can start to look at those patients that have got a higher likelihood of being a long waiter using all their underlying features. I mean, some of it might be known to the service anyway, but over a large set of features, this then can predict whether a patient's going to be a long waiter or not. And then it gives them, if this is on the first day of their inpatient spell, gives them another 6 days to act on those predictions. So how often to retrain is another question I've been asked on a lot of machine learning courses. Again, it's down to the local knowledge, but a lot of the time the patterns, the underlying real interactions that the algorithm picks up don't change that often, interestingly enough. So daily retraining will probably be a use of a waste of resources. However, it's useful to train on a kind of weekly basis, so whether it be Monday morning or Friday afternoon or whatever, to then build the next model. And then the model training needs to then be factored into the machine learning pipeline that you then undertake. Essentially, then that's how you deploy a supervised machine learning classification solution and then make predictions with unseen data. We've also trained a regression algorithm, but that needs a little bit more work in terms of feature inclusion, so looking at the features that need to be included. I'll skip back now to the presentation because there's a few other things that I'd like to cover. So why do I use Caret in this instance, and why do I still think it's very useful for the NHS services, and why we use it a lot with our customers? So deep learning can be more effective. So packages such as Keras, TensorFlow, H2O and MXNet are used for different reasons, and we've used them for different reasons. However, most NHS systems, if you've got a highly dimensional data set with a lot of records, they don't have the servers that can deal with the processing load needed for these deep learning algorithms. Furthermore, if you were to use cloud-based like Amazon Web Solutions and Amazon Web Machine Learning Solutions, we've got a lot of data governance issues there that we still need to get around. So Caret's the right fit. It's like the porridge in between. It's the nice middle ground between that more deep, serious machine learning and the applications that can be useful on smaller and medium data sets. And it's really, like I say, it's written in a real standardized fashion, so it can be deployed in a lot of applications. And again, there's just a few scenarios whereby you could use machine learning with your problems that you're trying to solve, but there's loads more that I've probably not explored. In terms of tidy models versus Caret, so there's a new wave of packages being created to work with your kind of non-standard evaluation, more tidyverse modeling concepts. Max Kuhn and his team have been developing this, and the two packages that are now being used as a kind of not replacement but in tandem are recipes and parsnip, but they've only got about 25%. So parsnip's only got about 25% of the algorithms that have been listed in that models list that I showed you previously. Max Kuhn admits himself that it's not a replacement for Caret, and it's still, up until when I wrote this, it's not got that much ensembling capability, and it's not going to be deprecated for a long time, so it's still really useful. Links to other cool work then. So feature importance, I've identified the global feature importance. Now you can use the function that I've created in your tools, but local feature importance is also really useful. So Lime's a great tool, and the guys there at the Crown project do a better job of explaining it than I will. In terms of parsnip and recipes, so there's a real good, it's about 35 minutes, a real good lecture from Max Kuhn on the advances in parsnip and recipes. I've put the YouTube link there to check it out. It's really worth a watch, and he also shows you how to build models in that session using the new tidyverse logic as well. In terms of speeding up your machine learning models in Caret, I did a blog post on NHSR community and on my own site. You can there's a couple of packages you can use that take advantage of threading, so using multiple processes at once to speed up your algorithms, and that's kind of halved some of the load times of the models that we've got deployed with certain trusts at Draper and Dash. And then what I've showed you, but in a little bit more depth, how you deploy a machine learning model in a production side environment. So you can follow the Draper and Dash link, which takes you to the deploying a trained supervised machine learning model. In terms of interest in deep learning, so I've covered Caret and supervised machine learning. If you're interested in deep learning, I've got a lot of experience working with H2O AI and Keras TensorFlow. So I'm happy to do a workshop or a tutorial on that. So in terms of signing off, and there will be a time for questions and answers, there's a link to my GitHub site. There's a link to the resources of the NHSR community as well. There's my website by clicking there. There's an email in case you've got any questions after the event. And there's my Twitter account. So that's probably monitored more than my email. So yeah, please feel free just to tweet me at StatsGary. But yeah, I'll then open it back up to the guys for any questions.
Thanks a lot for that, Gary. So I've got a question myself here, and I think one of the kind of issues with the kind of machine learning particularly is it's a pretty daunting field to get into. There's 1,000,001 algorithms that you've just mentioned there, and it's kind of hard to know which algorithm to learn and which ones to use in which situation. Do you think you need to learn all of the theory first, or can you just dive in and learn a little bit about pick random forests and build a model with that and have a go? Or what are your thoughts are?
I think you've got two camps here. So you'll approach it from the purists, so the kind of mathematicians, statisticians will want to know the underlying theory and logic. Thus why it's good to check out the introduction to statistical learning if you're trying to get into that, because that handholds you through the process and it'll explain all the algorithms in depth. If you're kind of into computer science and you want to just get the best algorithm for your particular problem, then the algorithmic benchmarking that I showed in the Caret tutorials is probably the best way to go. So don't feel daunted. I think you just need a problem to try and solve and start working and iterating through it. And like you say, I'm happy to work with anyone if they've got any particular solutions that they're trying to implement. But yeah, don't be put off by it. There are a lot of algorithms. You don't need to know them all. If you're approaching it from a computer science perspective, then you're more likely to be a bit more gung-ho. If you're a statistician, then there are supplementary resources that I've put a link in to on my presentation.
Great, thanks a lot for that. So we've just briefly shared in the chat the link to the Mentimeter for feedback. It'd be really useful for all of you to fill that in and just let us know what how you thought the session went, what you kind of want to see in the future. Have there been any kind of technical issues that we are not aware of? It'll really help us improve any of the future sessions that we're doing. So just to remind you all that we are planning to do webinars every third Wednesday of the month. Alicia, please shout at me if I'm getting this wrong. And we will be announcing on Slack and Twitter the upcoming events as they are ready and available to sign up for. The other thing is, so we're not going to have an in-person conference this year in November like we had the previous 2 years, unfortunately. But we are planning to run some kind of virtual conference or series of webinars. Details are kind of yet to be ironed out on what that's going to look like, but that'll be at a similar time in November, so keep your eyes peeled for that. But we've had a question or two come in now, Gary, so
excellent.
Yeah, we've had someone comment that they'd be really interested in a session about H2O as they're thinking of implementing that at their trust, so that's really interesting. Yeah,
I think we need more workshop for that kind of in an hour. It's probably a lot to cover in an hour, but yeah, I mean we could think about a workshop going forward, and I'll talk to Tom and the guys around how we arrange that.
Cool. Yeah, I've played a little bit with Caret rather than H2O, so I'll be really interested to see what all the different packages that are available and see how they compare.
H2O's got a real good cloud offering as well, so it kind of complements that. I mean, I know Caret and TensorFlow are really great packages, but yeah, they've got a massive cloud wraparound for H2O AI as well, so it makes it a real competitor, and it's been around actually longer than Caret and TensorFlow. I mean, it was one of the first deep learning packages to come into. I think it was C++ initially, and then it's migrated to R and Python. So yeah, I'm happy to run that.
Great. And we've just had a general comment that someone's finding all the sessions really useful and inspiring. So thank you, Gary.
You're welcome. Very welcome.
So we've got a question here about what hardware environment would you recommend for running Caret models that's likely to be available within the NHS? How long would you expect training runs to take? So just as a little aside here, I had an issue a couple of weeks ago trying to run a random forest model, and the first person I reached out to was Gary on our Slack workspace, and he immediately responded and absolutely helped me make the model run within a reasonable amount of time. So yeah, thanks a lot, Gary.
About machine learning is until you've run it once, you don't know how long it's going to take to run again. So with certain, especially with regression models, they can take a lot longer than obviously classification. So if it's a binary classification that you're trying to output, so whether it belongs to a certain class or a certain probability, they run really quickly. So you're probably talking in a massive data set. So I did one around about 60, 70,000 with 100 features. That kind of trained in under 15 minutes. If it's a regression algorithm, there's loads of differences, so there's a lot of variance between the things you're trying to predict. Then yeah, you can lose a day easily. So it's worth. Again, there's no hard science here, but that's why I put in my code, always put system.time when you run the algorithms, because then you've got a benchmark for running it again.
I think I've learned as I'm playing about with his, try not to be too enthusiastic at the start. Maybe take like a sample of your data set, just see, you know that it's not going to give you reasonable results, but if you take 1,000 rows and it takes 10 hours to run, then you know that you're going to have a problem when you try and run it with 10,000 rows.
Yeah, and if that's just a simple train and test split, like we showed in the initial classification part, if you then try and do repeated cross validation, so repeating that over and over again, yeah, if it's already taking what 3 or 4 hours, that's probably going to eat about 12 hours of trading time. But yeah, I would say that like Tom said, do a subset of the data and see how. I'd say take 25% of the data in terms of training, see how long that takes, and then do a subsplit of the 25%. So a training and test sample of that, see how long that takes, and then if that's pretty quick, you can up the ante a little bit. But yeah, I mean, this is something that my CEO asks me quite regularly. We don't know until we've run it, because we're doing a lot of new projects all the time. We have to get a baseline, so we have to run the algorithm first to establish that baseline. I hope that kind of answers the question.
Yeah, I think so. I think that there was a little bit of a follow-up there about what will be available within the NHS, and I think that it's a really hard question to answer. That one is because some of this stuff, like, especially if we're talking about H2O or Caret, then you're going to be talking about having very high-end kind of machine learning workstations, and they only really exist in the cloud because you're not going to throw tens of thousands of pounds of graphics hardware into an NHS data center. But a lot of this stuff, it will run on your own computer, won't it? You'll start reaching a certain point where you need more memory and CPU, but
RAM, but it's just your RAM really for Caret. I would think that you'd probably need to upgrade. I mean, a GPU always helps, but yeah, you definitely need GPUs for TensorFlow and H2O. That's something you definitely need to factor into your hardware considerations.
So next couple of questions that have come in. When using random forest, would you always recommend scaling predicted variables?
Yes, always.
Nice and quick, short answer.
Because that's going to improve training time as well. And if you're taking a copy of the original data and then scaling that, you can always bind the labels back onto the original data. So you've got the original values before they were scaled. And we've had another person that really wants a TensorFlow webinar, so definitely we're going to be doing something deep learning in the future. Yeah, I mean, happy to run that. We could do it as a 2-day session or a half day on H2 and a half day on TensorFlow.
Great. So next question. In the comparison and regression methods, the neural net performed poorly against standard regression, but you can set up neural network to perform no worse than standard regression. Does this mean that Caret defaults aren't very good?
The Caret's ANN, yeah, the defaults aren't great in the artificial neural network. You'd have to really tailor the artificial neural net. I mean, actually, I've tried it though to get it to perform as good as a random forest, and on some of these data sets, it just won't. In Caret, it won't work very well. You'd need to expose hidden neurons in a deep learning kind of TensorFlow H2O kind of setup to try and get that to work. But then again, the more hidden neurons that you expose, the more time it's going to take to train, and then the more need for higher intensity machines. Yeah. So the answer to the questions, yeah, the defaults aren't great.
Deep learning, it seems a bit of a dark art at the best of times, doesn't it? So.
Yeah, well, if you're assuming a simple ANA, and then it's a bit like linear regression, but when you start putting all the activation functions in, then yeah, as long as you know what you're activating at what point, you need to then understand a little bit of the background mathematics, but not at all. It's just you run it and see what it comes up with. again, if you want to understand everything, then I think you need to be a professor of a lot of different disciplines. Not to be rude, but they are quite advanced. Jeff Hinton's done quite a lot of interesting webinars on neural networks, because he's like kind of founding father of the dropout method and stuff like that. So if you come on the deep learning course, I'll explain to you why that's important.
Got a couple of things that I think we can probably answer very quickly. How did you arrive at tenfold validation? And that's really just kind of something that is a bit of an industry almost standard, isn't it? That people pick like 5 or 10. I don't think it really matters, but tenfold is. You've got to understand. There's a mixture between your statistics, your science, and how the computer algorithms are formed. Some of it is your own intuition, and some of it's a little bit more of an art, I would say. So that's more of a subjective decision. But yeah, I think Tom's right. There's a lot of research to suggest that actually you get no more return on accuracy past tenfolds. That's quite a common cited bit of research. And the next kind of question was there any brute force behind the scene? I think that kind of means like just playing about with some of the parameters and things, your hyperparameters.
Well, yeah, I mean, the hyperparameter tuning uses gradient descent. I mean, feel free to look up gradient descent. It is covered in the Introduction to Statistical Learning book. That's the only kind of tuning that we've done as part of the process. But yeah, I mean, even with standard algorithms and just taking it through that very simple workflow, we've got really good estimates on that.
So next one, how do the Caret ensemble methods choose their weighting of the models?
So the weights of the models, so how they vote.
Yes.
So there's a lot of mathematics underpinning this. Again, it's available in the Introduction to Statistical Learning, but I think it's average voting. There's the Caret default. You can set that. Different because there's weighted voting and there's average, max, and there's loads of different types. But yeah, I think it's average voting that it uses as its default.
So someone's asking about your 2-day workshop into modelling. So I suggest on that if you share any of your kind of upcoming courses that you offer on that in Slack, that would probably be the best way of going forwards. Give yourself a bit of free advertising there. So what's your opinion on model-based ML approaches as opposed to the more traditional approaches you've described here? Spoke to a senior Microsoft ML engineer at a conference. He basically said, either use deep learning if you've got enough data, and if not, then use model-based ML. Don't use any of the traditional approaches such as random forest. They're not really worth your time. Sounded like a very controversial statement at the time, but haven't had the chance yet to look into model-based ML.
Yeah, I certainly agree with the guy from Microsoft. I mean, if you've got enough data, so you've got enough underlying presence in the features, then deep learning is definitely the way to go. I wouldn't discount random forests. I mean, model-based approaches are very useful, but I wouldn't discount random forests and traditional statistical algorithms either. I mean, machine learning, deep learning is the future. So we're all in the intense time of mining lots and lots of data. It's going to be the only way that we can distinguish those patterns. And there's been lots of breakthroughs in different areas like convolutional neural networks, so the ability to detect photos and images and create surveillance systems. Like, I don't know if you heard something about generative adversarial networks. They can take music that they've learned and compose unique pieces. They can compose art. I mean, there's lots of stuff that's happening with deep learning. In terms of the traditional learning, I still think it's really useful in terms of a model-based approach for implementation to the NHS, and it does give you useful things that do augment decisions and do support decision-making processes. So I never say that algorithms are going to replace people. They're just to augment our intelligence and probably just replace some of the boring tasks.